I'm Tejas.
I'm Benjamin.
I'm Sam.
I'm Wendy.
And we are students from Bellevue College who've spent the past 6 months researching reinforcement learning in a real-world, real-time environment. Now, in the beginning, there was AlphaGo. AlphaGo beat some of the top Go players in the world, and it really put the idea of reinforcement learning on the map for the general public, the whole buzzword reinforcement learning. And we were really interested in this. We said, wow, this is fascinating. But we realized that Google has unlimited resources, we don't, but we still wanted to do some interesting research. So we decided to double down on our lack of resources and decided to test the feasibility of reinforcement learning in a limited setting. So we took a sphere of one, which is this, and taught it to avoid obstacles. Now, the interesting limitations of our project was that the sphere of one doesn't really have a lot of sensors. It doesn't have vision, it doesn't have proximity sensors. All it has is collision data and velocity. Second, we did not use any kind of cloud computing. It's just consumer-grade laptops, that's it. And third, no simulations. No trying to make the process of learning faster. Just real world, real time, that's it. So to discuss the specifics, I'll have them help me.
Thanks, Pages, for that introductions. So what I will be talking about is the tools and resources that we use to answer our research questions. So let's talk about the experimental setup. We had an agent that had an axis space that chooses velocity and heading. The velocities it can choose from is from 0 to 255, and the heading had 360 degrees of motion. What can the agent learn from the environment? Well, it had observation data that looked at position, its velocity, the magnitude of the collisions, and the number of collisions. And how we decided to calculate coordinates, looking at the max number of velocities, we subtracted that from the number of collisions. And so given all this data, how do we make our agent learn? We decided to use something called DQN, DQ networking. The basis of DQN is looking at action value functions that dictate the behaviors and actions of an agent within an environment. An action value function is basically a numerical number that determines how good an agent, how good an action is within a given state. And essentially what a DQN is, it starts off by initializing these action value functions. It interacts with the environment, it looks at its observations, and based on those observations, it updates the action value functions in the binary network, and it cycles through throughout the end. And by the end of this cycle, we're hoping that our agent has a better understanding of the environment, something similar to this. This is a very simplified version of a DQN, but you can kind of get a sense of like every state, every action within a state has an action value function that tells how good it is. It's kind of like a very complicated game. Am I hot? Am I cold? So why did we choose DQN? We had a lot of models to choose from, one being Actor Critic. Actor Critic requires multiple agents to update your neural network, and we didn't have that function, so we stuck with it. So how do we tune our algorithm to have better and optimal learning conditions? Well, we looked at changing our parameters. The parameters that we looked at was the collision sensitivity. We looked at low velocity penalty, making sure our agent was moving. And then we looked at how to change our rewards by looking at the collision penalty multiplier and the velocity multiplier. And then we also looked at hyperparameters as well, that looked at how to change the algorithm and how it's learning, whether or not we chose randomized actions or we based on what actually is happens. So I'm gonna pass off to Sam to talk about it.
Thank you, Megan. All right, so given all this theory, all these numbers to tweak, we just wanted to see what this thing would look like. What would happen when we put our little dynamic sphero in a 2 feet by 2 feet wooden box, how to make 200 decisions per episode, train it for hundreds of episodes, and hope to see that we see an improvement in its rewards. And as you can see, it did. It figured out how to get a little better behavior, get better, more numbers. Pretty cool. But as you can see from these outliers, there's a small bug in our code where it figured out that if it rolled against the wall, it would think it was moving. So it would get these massive rewards. So it thought it was worth it to just climb up the wall and get those big rewards. So that was so good. And considering the 92,000 different actions it could take in each step based on all the directions, that was a little too much for our consumer-based laptops to handle. So we scaled down the number of directions to 8 directions, 15 different speeds. We increased the collision penalty multiplier to 1,000 so that the walls are like lava. Don't touch them, please. And we reset the sphere to the middle every time it hit the wall. So it wouldn't make 200 decisions every episode. Hit the wall, put it back to the center. And this showed some improvement in its behavior. It stayed center, moved around a bit, but still not quite as much good behavior as we wanted or as improvement in growth. And on top of that, it figured how to cheat again, where it would slowly waddle up towards the wall and then start getting those big rewards. This is what the data looks like from that, where a good behavior was negative 60,000, so maybe we went crazy on the penalty multiplier. So we want to encourage more control in its behavior. And I'll pass it off to Wendy to show the final product.
Yeah, so for our second attempt, we limit the max speed to 50 and the number of directions the squirrel can take. We hope this will improve the computation time, because on the previous training, we noticed that it takes a while for the model to update the weights in the neural network. We also lowered the collision penalty to 20 from 1,000 and train a lot more episodes this time, more than 1,000 episodes. And each time we reset the squirrel back to the center after the collision. And here's the video of the latest results. As you can see, the squirrel is moving around, getting more positive rewards while trying to avoid collision, which is a good sign to see. And here is our data. As you can see, there's still a little bit more negative and few positive, but as you can see, the regression line is heading toward more positive results, and which we are really excited to see, not just on the data, but also on the physical, the environment we see. And this episode is from 1,200 to 1,375 episodes. Yeah, I'm really happy to see these results. And I'll pass the to finish the rest.
All right, so to conclude, let's go back to our research question of feasibility, reinforcement learning, and a limited setting. So a good portion of the training that we did was problematic. The results we had were great. So we had to reset it every single time by putting it in the center every time there was a collision. So that was inefficient. The part when we were able to the corner and try to collect the reward, like a lot, that was also bad. And then there was also the problem of misleading data. So the data showed that it was good, but observational data was not good. As you can see, in the beginning, we roll into the corner, just keep on rolling. And then most recently, we did find a solution, which we plan to build upon, where right now it's moving around and trying to avoid the rolls. Not the greatest, but it's still somewhat of a solution. So in the future, what we want to do is we want to expedite the training by going back to the issue of basically the center every single time. So instead, place it one time in the center, let it train from there. In addition to that, we want to increase the memory buffer so that the sphero can look back into the past, farther into the past, and then hopefully it'll learn quicker from that. And then in addition to that, we want to increase the number of episodes that it trains for so that it'll yield more results. And then lastly, to account for the observational data that we have, we want to record the number of steps that it's actually taking per episode. With that, we want to acknowledge Casey Irvine, coach, Michael Reese, and Christina Severa. But for now, let's open up for Q&A. If you have any questions.
Before questions, Timothy, and then questions.
So there's the traditional algorithm tree learning that you have to do. So is the only difference between these two the machine learning part that you trained it on a neural network? And what was the exploration function that you used?
Sorry, can you say that again?
So what's the difference between the equivalent and the Q learning part? And what was your exploration function?
Yeah, that's a great question. So Q learning uses a tabular Q learning, right? It doesn't really use a neural network. And the reason why we wanted to use DQN and neural network was because our action space had 360 degrees of motion. Well, typically a Q learning table has a really small data set and just we wanted to use DQN. And so the main difference is the neural network. That's the first part.
And the exploration function.
Exploration.
What was your exploration?
Oh, the epsilon?
Was it epsilon maybe?
Yeah, it was.
Yes.
It was absolutely.
I think the original equivalent paper they use like some convolution networks to extract some visual features and process those different layers. But so in your settings, you say that you have a tons of state space and then you use equivalent. Could you describe in detail about like how you actually apply equivalent? Do you still use like visual features from some factors or?
So you're asking if the data we're taking is from visual?
Yeah.
Oh no, like all we had was it knew its movement position and when it collided with something. Like that was all the data we can gather from it. So pretty much we're just trying to map the environment and behavior just based on things.
So just normally like because I know the original DQN is basically using convolution network on some visual input, especially it's playing the output game. So how you actually apply DQN on this physical environment? Maybe it's
That's a great question.
Yeah.
I'm not too knowledgeable about the convolution layers.
So convolutional images, we have no input with images at all. The only input that we had was collisions if it hit a wall, like how hard it was hitting a wall, its acceleration, so its velocity, its speed, and then basically it's like position of where it thought its position was. So that's why we had the issue of it rolling into the wall. Just trying to keep on rolling, so we have to reset every single time. But the reason it works with DQN is because DQN, the inputs were basically numerical.
I think we have to take it offline if you guys want to talk about it. Otherwise, thank you.